Hey, yo, what's up? Today we're going to be talking about extreme calculus, extreme applications of calculus, extrema, relative and absolute, two types we're going to be dealing with. So if you remember to our kind of introductory video to concavity, intervals of increasing and decreasing, critical numbers, we're going to be talking about those things today. Not really about concavity. That'll be in a later video. But we're going to be talking about these. There's a bug on my whiteboard. We're going to be talking about these relative and absolute extrema, peaks and valleys of a function, and we can use calculus to find these and define them. So I'll do a little bit of that here. Relative extrema. I'll give you like a little bit of a definition. I'll draw out some examples for each. Absolute and relative. So a relative extrema is going to be higher or lower than points, PTS here, on either side, right? And I'm going to also kind of highlight this word here, local. That'll be important in a second. All right, kind of wrote that one right. It's tough to see. All right, relative extrema, higher and lower than both points. Points on either side, sorry there. And they're local. And so it's kind of a more textbook definition. Show you what that means here. I'll draw out this interesting function. Okay, so when we're talking about extrema and local extrema, relative extrema, right, what we mean here are going to be these kind of areas of our function that are super easy to spot, that kind of make defining shapes. For example, here, this peak, this valley, this peak. These are all going to be locations of relative extrema, right? They are the highest points in this kind of little area, right? So this right here, this spot, those can't be extrema because they are not higher or lower than both points on either side, right? However, up here, this peak, that is a relative maximum. And here we have a relative minimum. But it is important to note that because of this kind of other side or both sides condition, these endpoints cannot be relative extrema. That is a important thing to note, right? However, if I were to draw this very, very similar here graph, we're going to go all the way up here. Graph for that I'm going to use later to demonstrate absolute extrema, right? First, we're going to clarify how does this all relate to calculus, right? Critical numbers, increasing and decreasing. It's really windy. Sorry if there's some background noise. But if you remember back to that video quite a while ago now, you remember critical number is defined as when the derivative of a function is equal to 0 or does not exist. But the important thing is that at critical numbers, your derivative could either be positive and stay positive, or your derivative can go from positive to negative, or just in general, switch signs. When your derivative switches signs at a critical number, some important things happen to a function, right? Say this is f of x as a function of x there, right? And that'll be the same for both of these graphs. So if this is f of x, we see here that at these relative extrema, you have you have critical numbers. Critical numbers in your derivative happening here. So I'm going to just say like f prime of x is going to equal 0 here, right? It's really going to equal 0. It's a little bit more difficult to tell if your derivative doesn't exist. For the most part, remember calculus is a study of continuous change. We're not really going to be dealing with discontinuous derivatives most of the time. But you do have to know that the or does not exist condition is a possibility for your critical numbers in your extrema. But for here, most likely f prime of x is probably equal to 0, right? This is some sort of polynomial function. This looks like it could be graph of a to the 5th, 4th, 6th, something like that, right? It's definitely even. Both the endpoints go down, right? So 4th or 6th. So most likely your derivative is going to be equal to 0 there. And then here, at these peaks too, your derivative is also probably going to be equal to 0. More specifically, when you have a peak, right? Think about, this is f of x, right? This is f of x, kind of this peak here. Now what is f prime of x doing? F prime of x here in red is positive, right? Function's increasing. Here, it's 0. You have a horizontal tangent. And now here, it's negative, decreasing. Your function is decreasing, your derivative is negative. So that's how calculus allows us to find extrema, right? If I were to give you a graph of a derivative, I'm going to go ahead and erase this. We don't need this anymore. I give you graph of f prime of x. And the graph of f prime of x, you know what? I should draw quadrants 1 and 4 here, right? Your derivative, let's say it looks like this. Goes, okay, maybe does something like that, right? This is a continuous derivative, meaning this function is differentiable at all points. Even though there's this sharp curve here, that would just mean the second derivative is not continuous. Or your derivative is not differentiable at this point here. We don't need to worry about that right now. We're worrying about these points here, where your derivative, f prime of x, is equal to 0, right? Here, these are both critical numbers. In this first critical number, our derivative goes from positive to negative. So we're going to have kind of a increase and then a decrease, where at this point here, it's going to hit 0, right? So we're going to spot that from our graphs. Here, we do have a critical number, but our derivative goes from negative to negative. So that doesn't really mean anything for our function in terms of extrema. That's not going to create an extrema, right? That will create another awkward little shape that we'll probably talk about later. I am so clumsy. Now, the same thing applies here. Let's say I drew this derivative such that it did cross the x-axis at this critical number, right? And then we'd go from negative to positive in our derivative, meaning our function f of x is going to be decreasing. Eventually, our derivative is going to hit 0 and then increase. So we're going to have a relative minimum, relative max, relative minimum. It's important that when you talk about extrema, you label them relative, or as we're about to talk about, absolute. Relative maximum, we're going to hit kind of a upwards arc. Relative minimum, we're going to hit kind of a downwards arc there. This has not much to do with concavity. Usually these peaks and valleys do deal with, or they do kind of correlate with concavity. As you see, concave down looks like frown, concave up looks like cut, right? Someone's calling me, I apologize. I have to decline that, talk to them later. Yes, so, and then I'm actually going to erase all this. We're going to prepare to talk about absolute extrema. And I'm also going to erase our textbook definition because now we've applied calculus to our extrema, as you might have seen just then. We're going to have a new kind of textbook definition. So for a valley, I'll call them, going to look like that. Your derivative goes from negative to positive, right? Somewhere in the middle, it's going to hit 0 because you're going to have that horizontal tangent. Your derivative is continuous, right? Yes, that is correct. Negative over here, positive over here, f prime of x. But for a peak, it's going to look something like that. F prime of x is going to go from positive to negative. Most likely hit 0 somewhere in the middle. So that's our calculus definition of a relative extrema, right? But now we have absolute extrema. Not as tricky, and I'm actually going to redraw this graph here to look something like this. This will make a bit more sense in a second. You still have these endpoints here. Function's not going on forever. But here, I could tell you that we have absolute extrema here and here, right? So your absolute extrema are really just going to be, and I'm not going to write this out because it's pretty self-explanatory, some sort of extrema that is the absolute lowest value of your function or absolute highest value. And that's talking about f of x value. So that's going to be up here and down here, right? Now, I'm going to go up here a little bit, draw another example. This is of f of x as well. Now let's say I just have a function, kind of a quadratic curve, that just goes up forever. Now, if this is an endpoint, okay, sure, this could be a absolute minimum, and but over here, this could not be an absolute maximum. Now in calculus, we deal with infinitesimals, infinity, all that stuff, infinitely small and large. Functions that go off to infinity in a direction are not going to have an absolute extrema in that direction. For example, this f of x function is not going to have an absolute maximum, an absolute highest value for this function, because it really just goes off to infinity forever, never ends, right? However, many times we can find absolute extrema on our function, right? This function has our absolute maximum up here. There are no arrows. If there was an arrow going up this way, there would be no absolute maximum. If there was an arrow going downwards, like let's say this function curved back around, whoop, there'd be no absolute minimum, but there would be an absolute maximum still, right? So these arrows are kind of conditional on only the direction they're pointed in. Absolute extrema are rather simple. It's kind of an extra step. If you're doing the math behind this, you could find still a critical number, right? When f prime of x equals 0 or does not exist. DNE there, right? That's still true. However, you generally, there are only a few instances where you can find an absolute extrema through not given a graph or function, just given a derivative, right? For example, and I'll erase this graph since we don't need it anymore. And since absolute extrema are so niche and kind of conditional, they're dependent on a lot of things. They don't really show up a whole ton in calculus. However, let's say you have a function with endpoints that has one peak. It has one singular peak. Now, if you find your critical number and you find that there's only one critical number on your function, and it's a peak, you're going to have that absolute maximum there, provided that your endpoints are lower than your peak. So there are, again, a lot of many conditions, but you can find that if there's only one relative extrema on your function, it could be an absolute extrema. And so I'm going to show you a little trick that I've used in my years of calculus that has helped many times. Might not be for everybody, but that's okay. I generally draw kind of a number line. It's weird that we're so far in math and we're using number lines like we did very far ago, or very long ago at the beginning of our mathematical journeys, right? And I like to kind of label f of x on the side, f prime of x, and eventually when we start dealing with concavity, we'll have that f double prime of x, but we're not going to deal with that today. We're not going to worry about that now. We're not going to really worry about inflection points like we introduced in that one video. Okay, so first we're going to find our critical numbers. We're going to get our f prime of x function equal to 0 or does not exist, which this is very uncommon, not very likely to happen. So really we're going to find where our derivative is equal to 0. Okay, now those are our critical numbers. I always like to list them. Critical numbers are going to happen at x values, input values, not output values, input values. So that's going to be, let's say, x equals 1 and 3 are critical numbers for our function. And this applies for all of extrema in calculus, not just absolute extrema. Sorry, I did not clarify there. Now I'm going to label these points on the number line. Now, if you think about what your derivative is doing, if your derivative, for example, I'll draw a graph over here. This is 1, this is 3. Your derivative, if it's equal to 0 at 1 and 3, now let's say it starts positive and then goes negative and then goes back up to positive again. Now, between these two zeros, it can only be either positive or negative. And we've proven that because at critical numbers, that is when they can switch. Your derivative cannot switch from positive to negative unless, or negative to positive, unless a critical number happens. And that is important because that is why this number line works and why this trick works. We are going to find values in between these inputs and beyond, right? This is going to be a negative infinity, this goes off to positive infinity, right? We're going to pick values between these critical numbers, between the critical numbers and infinities, right? And we're going to determine the sign of the derivative, and that's going to tell us things about our function, right? So I'm going to use this as an example, right? We can pick any value between x equals 1 and x equals 3. Here, I'll show you, and this will start to make sense. It'll all click, right? Let's pick x equals 2. What happens at x equals 2, right? Well, usually we'll be given a derivative. We'll be given f prime of x, and this is f prime of x, by the way, this graph, is going to be equal to something, right? We pick a point. We're going to say f prime of 2 is equal to, okay, it's going to be equal to some number, right? We just found a slope. But that slope is always going to be negative, as proven by kind of our reasoning here. Your derivative can only change signs at critical numbers. And if we know that we are between two critical numbers, that our derivative is going to be of the same sign condition the entire interval, right? Same here before x equals 1, same after x equals 3. So that's important. We found that f prime of 2 is going to be equal to some negative number. We don't really care what that number is. We just need to know that's negative, right? We could pick anything. We could pick f prime of 1.5, f prime of 2.5, any value between 1 and 3, right? But we find f prime of 2 is a negative number, right? So I always kind of like to draw these out next to the f prime of x function, create like a little table here almost, right? So since f prime of x is negative, f of x is decreasing, right? And I'm going to go ahead and erase f double prime because we're not going to use that, right? And I'll erase this critical number stuff down here since we know our critical numbers. All right. Now we're going to do the same thing for all of our intervals. We have to do this for all of our intervals to find all of our extrema. The end goal of this is to find what kind of extrema we have, if any, right? Now, let's say over here, we find f prime of x equals 0, right? Because we can choose any value left of 1, x equals 1. We don't have to go super far out, just any value before this critical number, because any value will give us the same sign, right? Now let's say we find f prime of 1 to be equal to a positive number. Okay, perfect. F prime of x is positive, meaning that f of x is increasing here, right? And I always like to kind of have another row on the table if we're like drawing, right? If f of x is increasing, it's going to look something like that, right? And then over here it's decreasing, boom. We know that this is our critical number. We know that f prime of 1, for example, oh, I wrote this wrong up here. F prime of 0 is a positive number. F prime of 1, I'm just going to say is equal to 0. Could not exist. I'm going to say it's equal to 0 for simplicity, right? We know that here it's f prime of x is equal to 0, right? Or, I keep messing up today. Sorry, guys. 0, right? Derivative. So already right away, what this tells us is that our function goes from increasing to decreasing. This is kind of a nice little visual for us to plot all of our things because we have to worry about a lot of stuff. We have to worry about critical numbers, what we're inputting to our derivative. We have to worry about what our function's doing, what our derivative is doing, and then what kind of the graph is doing if you need to visualize that, right? Now, let's ignore this, for example. And let's say that we have a critical number here at x equals 3. And I'm going to choose x equals 4 to plug into the derivative. Now, let's say we plug in x equals 4, or just rather f prime of 4 to our derivative, right? Our derivative is given to us usually, or we find it given a function, right? We can take derivatives, we know how to do that, right? Let's say that's a negative number. Ooh, okay. Let's say it's a negative number. So f prime of x is negative, meaning f of x is decreasing. And if I were to draw that out, again, I'd kind of draw some sort of decreasing graph, usually with some sort of concavity. That helps, because usually our peaks and valleys kind of are concave, right? But this doesn't tell anything, or this doesn't tell us anything about extrema, because if we're going from decreasing to decreasing, we don't have an extrema. So there's no extrema right here, but there is here at x equals 1, right? And so that's kind of a nice little example for, not example, my apologies, nice little method for finding your extrema on your functions. This is a little bit complicated, and so I might release kind of a video short video of me doing some math on a piece of paper where I start off with a function, take its derivative, and then find intervals of increasing, decreasing, and find relative extrema, right? Absolute extrema, more so just need to know about those, less so how to find them. If you do, I guess, let me know. I've never ran into really people super strict about finding all the absolute extrema. Relative extrema are very important in calculus, though. This is one of our biggest applications of derivatives, at least for now, right? Don't mean to scare you or anything. So anyways, if this doesn't make sense, I'll probably release another video. I know this is pretty complicated and I went really fast. Didn't really have any specifics with function values or anything. So thank you for joining me for this video about relative and absolute extrema, extreme calculus. Goodbye.